This is Sagar from Rensselaer Polytechnic Institute in Troy, New York, and I do research under Professor Mottaleb. The main topic of my research is analog integrated circuit design for optical communication, and as part of my research, we also collaborate with University of New Mexico for device research. So this talk is about speed optimized large area avalanche photodetectors for visible light communication, and these are the topics that I'm going to cover. First, the motivation for optical communication and the challenges for high speed optical communication in the specific application area that we are looking at, and then I'm going to introduce some relevant prior work. Then I'm going to propose the structure, and then present some simulation and measurement results before concluding. So the motivation for optical communication is has been discussed over the years, and some of the advantages over optical communication versus RF communication is higher bandwidth, lower electromagnetic interference, and of course the frequency band is unrestricted, unlike the RF. So the communication differences in optical and RF is just the channel. Of course, depending on the channel and the kind of modulation, the circuit and the devices has to be optimized. Another advantages of optical communication is obvious, like in hospitals or in aircrafts where the RFs are not appreciated, or they try to restrict RF communication there. Some of the application for one application for optical communication is obviously the fiber optic communication for long haul distance. Some of the applications that has been gaining momentum recently is visible light communication over wireless optical channel, and also using plastic optical fiber communication, where they use mainly in the infrared frequency band wavelength, for example in 600 nanometer. So you can see that in indoor and outdoor visible light communication with LED lights being modulated at the top is gaining momentum for wireless optical communication in indoor scenario or outdoor scenario. And there is something called home area network, multimedia optical communication inside car, and industrial automation application, where they try to keep the cost low and at the same time achieve high speed communication. So due to the reason that they want to keep the cost low, the main cost in the receiver side comes from the alignment of the optics and the optics itself. So to reduce the cost in that area, they try to increase the receiver photodiode size, so that the constraint of the optics, the concentrating power is these kind of things are reduced. And for fiber communication, generally the main cost comes from the maintenance, the alignment, and the fixing of the structures to have the best coupling efficiency is the factors. So for this kind of communication, which is called the plastic optic fiber communication, just a regular office knife can be used to cut the fiber, and then it's just called a carton plug that does not require any special handling. You can see that the difference, even though these pictures are not in scale, the difference in the fiber core diameter is actually huge with respect to the conventional optical fiber communication. So what are the implications of these things? The first thing is that for large area, due to the large optical fiber diameter, the photodiode has to be large, and due to the large area, the photodiode capacitance is high. And at the same time, there is another limitation of the photodiode itself. That is the intrinsic limitation that results in a limited optical bandwidth. It's not an electrical bandwidth. So we have an optical bandwidth limitation and an electrical bandwidth limitation. The electrical bandwidth limitation comes from the pole arising from the photodiode capacitance and the input impedance that you can see looking at the next stage. with some sophisticated analog technique, these input impedance can actually be reduced, and this is a simulation results of the transimpedance amplifier proposed in this paper in 130mm technology, and you can see that the input impedance can actually be really low as 5 ohm or even less than that with optimized design. So for the typical capacitance in standard CMOS technology, for the typical sizes of photodetectors, the main limitation comes actually from the optical bandwidth of the photodetector. So with the exponentially increasing data rate for internet traffic, mainly due to the video data, we need higher and higher bandwidth, higher and higher speed from the receiver side, and at the same time, for wireless optical communication and also for fiber optic communication, it's beneficial to have a receiver that has higher responsivity or higher sensitivity. So you can see that as you move away from the location of the transmitter, if the transmitter is not diffused in a living room scenario, the received power can actually be really low. So for this reason, we need high bandwidth and at the same time high sensitivity. To relax the sensitivity requirement from the circuit, you can remove some of the gain from the circuit to the photodetector, which is we need something like Avalanche Photodetector. So previously, Avalanche Photodetector has been proposed, and there has been different demonstrations and publication. One structure that is particularly beneficial or useful for integration is the P plus annual P substrate structure. This structure is fully compatible with CMOS technology, and the reason why this structure is better than just a annual P substrate structure can be divided into two parts. The first reason is that this structure is actually really fast. The main reason is the substrate generated electrons due to the illumination mainly are absorbed by the annual junction or annual connector. So you can say that this P plus annual photodetector is actually shielded from these slow diffusive carriers. The another reason for integration, which is actually more important for having this photodiode and the circuit in the same substrate, is that for annual P substrate structure, you have to connect the annual directly to the amplifier and at the same time apply high bias. So to protect your circuit from being burnt out due to the high bias voltage for avalanche action, you have to have something like AC coupling and separate biasing for this photodetector. But for this structure, you can just directly connect to amplifier and apply the reverse bias on the annual junction and have your circuit designs simplified. This is the equivalent circuit for this photodetector that has been proposed in this paper as a prior art, and there are different meanings of these parameters that you can find in these papers. Basically, this capacitance is due to the junction capacitance, and this light dependent small signal current is has a intrinsic bandwidth which is the optical bandwidth, and then these are due to avalanche actions, and this inductor resistance and this resistance does not depend on the area. It's a parameter of the kind of material you use. So the limitation of this kind of structure has been designed mainly for single core diameter or multi-mode fiber, single mode fiber or multi-mode fiber, which are below 50 micron diameter. So that's why the size of the photodetector did not have to be increased. But since we are looking at an application that has larger area, the limitation can actually arise from the transit time of the diffusive carriers, photogenerated diffusive carriers in the lateral path. So it has been also studied in these papers that when you increase the size of the photodetectors, this transit time of the diffusive carriers increases, and that actually reduces the bandwidth of the whole structure, which is actually the optical bandwidth that can be represented by this FTR. So you can see that this is d square here in this equation is actually the effective diffusion distance, which can also be in the lateral or in the vertical direction, and this is dominated by the lateral diffusion path. To overcome this problem, we have proposed to subsection the P plus annual junction and insert N plus connectors in between, so that the lateral diffusion path for the carriers are reduced. If you work through the arrows here, you can see that this is the equivalent circuit for this kind of structure, and ignoring the fill factor due to inserting these connectors or dividing the structure, assuming that the areas are same, and ignoring the sidewall capacitance in these large area photodetectors, you can say that the capacitance has been divided by n times. N is the number of subsection, and the photocurrent has also been divided by n times. But since they are in parallel, since the currents are adding and also the capacitances, the end results for the photocurrent and the capacitance are the same, assuming that there is no phase difference between these subsections. But the main difference in here is that since the subsections are smaller, the intrinsic photodiode speed due to the diffusion length of the photocarriers are the bandwidth are higher, and the transit time is lower. So the only difference between this structure and this structure, with all those assumptions, is that the transit time limited optical bandwidth is higher in this structure. So we have fabricated this structure with a APD area of 350 by 350 micrometer square in 0.3 micrometer technology, 0.13 micrometer technology, and we have also simulated some of the things that we measured or we could not measure. So this is the simulated dark current characteristics and the measured. You can see that the dark current increases when you are closing to the reverse bias voltage. The reason is that the increased probability of localized electric field in large area avalanche photodetector, that is also explained in one of the references. And this is the calculated gain and measured gain for a 4.5 milliwatt per centimeter square illumination. And dead space multiplication theory proposed by the UNM has been used for calculating these values. For the excess noise factor, we used the same dead space multiplication theory. The reason why we need this excess noise factor is that for a certain input referred noise from the circuit, there, if this equation is satisfied, then using a APD instead of a PIN junction photodetector actually makes sense. If the noise from the APD is too much, that overwhelms the noise from the circuit, it doesn't make sense to use APDs. So this excess noise factor appears in this equation, and you need to determine the leverage that you are getting by using the APD. For simulation of the small signal bandwidth, we used Medici, the 2D device simulator. The reason why we cannot measure it is that since the photodetector is large in area and we did not have the actual circuit fabricated that time, we had to simulate it. So these are the conclusions that I have to draw, is that the proposed technique can actually enable large area CMOS APDs in high speed applications for the advantages that I have explained. And I have to acknowledge to NSF and NISTER, New York NISTER contract for this work. Thank you.